Okay, I'm going to show the solution for a synchronous TDM multiplexing problem. And in this multiplexing problem, we've got 4 inputs with a rate of 450 kilobits per second, and then 1, 2, 3 inputs with a rate of 900 kilobits per second. We're going to assume no framing bits, and we're going to have no empty time slots. And so I've already solved this problem here, and so I can just walk you through it. Here I'm showing the 4 inputs A, B, C, and D with a rate of 450, and then 3 more E, F, and G with a rate of 900. And they are brought into a multiplexer and multiplexed into a single data stream with a bit rate R total. And so here's a picture, and including the frame design, what I've done was I've assumed, let's take the amount of time that it takes for 1 bit from source A to arrive. Well, that's also the amount of time for 1 bit from sources B, C, and D. So I'm going to have an A and a B and a C and a D. But sources E, F, and G are at twice the data rate, and so in that same amount of time, we get 2 pieces of data from E and 2 from F and 2 from G. E, F, and G. So I've designed a frame here that's A, B, C, D, E, E, F, F, G, G. And if we were doing bitwise interleaving, each of these would be a bit. Each letter would represent a bit, and we would have 10 bits. But we are doing bytewise interleaving here, so each of these represents a byte. And so we have 10 bytes altogether. 4 from A, B, C, and D, and then 6 from E, F, and G. Okay, so there's my frame design. And the total data rate, because we don't have any framing bits, is just the sum of the input rates, and you can add that up, and it really results in 4.5 megabits per second, 4 times 450 plus 3 times the 900. The multiplex signal's frame size, assuming bytewise interleaving, is 10 bytes or 80 bits. And finally, the multiplex signal's frame rate. Here's where it's a little bit tricky, I suppose, when you have multiple different frame rates coming into the multiplexer. If they all have the same frame rate, then you can always calculate the frame rate. If they all have the same bit rate coming into the multiplexer, you can always calculate the frame rate as the data rate of one of the inputs divided by the number of bits in the frame from each input. But here they're different, and so we have different ends for different inputs. So I'm going to call these inputs 1 through 7, I guess. And the first 4, we have 8 bits from each of those 4, because we're doing bytewise interleaving, and we have 1 byte from each. But frames, or inputs 5, 6, and 7, we have 2 bytes from each of those, so n is equal to 16 for those values. And what we must have is a consistent value for the frame rate. It must equal the rate of input 1 divided by the number of bits in the frame from input 1. It must also equal the rate of input 2 divided by the number of bits from input 2 in the frame. And for the n equals 1, 2, 3, and 4, we have 450 divided by 8. For n is 5, 6, and 7, we have 900 divided by 16. And so, of course, these two are equal, and it yields 56.25 kiloframes per second. The numerator here is bits per second. The denominator is bits per frame, yielding frames per second. And this gives us a good check that we've designed our frame correctly. If for every different input we can make this division, the rate divided by the number of bits in the frame, they're all equal to the same value, then we've done it correctly. Okay, hope this helps.